Hello, my name is Tristan Falck, student number 218004699. For my honours project, I have implemented a deep Q learning agent system and have explored the potentiality of preloading such an agent's replay memory buffer prior to its deployment within its environment. Moving over to the project itself, we see the game Snake on the left-hand side. On its own, this is far from impressive. The game, however, is not being played by a human. Rather, it is being played by a deep reinforcement learning agent which has no access to a transition model or any other information about the rules of the game. The agent has learned to play the game entirely through reward and punishment signals received from the environment. The primary neural network used in controlling the agent's actions is visible at the top right of the screen. As a broad outline of Q learning, it is a reinforcement learning algorithm which approximates Q values through the Bellman equation, as shown here. Q values estimate the utility of taking an action within a given state. Deep Q learning, initially proposed by DeepMind in 2013, performs this Q value approximation through neural network technologies. Shown here is the deep Q learning algorithm. Two neural networks and a so-called experience replay memory buffer, which we will explore in more detail shortly, are constituent to the agent. Should you wish to consider this algorithm in further detail, I encourage you to pause the video. While we can see directly where the snake and food objects are within the game, the neural network and deep learning system have a different view of the environment. Specifically, they are shown the cardinal direction of the food relative to the snake, whether they are in immediate danger, and what their current direction is. This state structure for the snake game, which could be compared to the dataset that would accompany a supervised learning problem, was proposed by Henny de Hard in 2020. The neural network then regresses the state into Q values for each action available to it, specifically which direction it should move. I will now pause the training of the activity of the network within the game. Once it's in a good position. Moving back to the project itself, we can see how the deep learning system's views line up with what we see. As we can see, the food is above the snake and to the right of it. When we move into the input layer of the network, we can see that the neurons corresponding to above and right in the first four neurons of the input layer are lit up, showing that the food is above and to the right of the network. Moreover, if we go to the output layer of the network, then the network believes that the best actions here are either to go up or right, as those Q values which it has regressed are positive. The other two values in the middle are negative, implying that the network believes it would be a bad idea to go left or down. This makes sense in the context which the snake is currently in. You may notice on the bottom right corner the rewards that the agent received undulating. Notice that if the snake dies, the reward drops into the negative, and if the snake gets food, the snake's reward spikes up. The reward structure used in this context is provided as follows. The exploration strategy used by the snake is the epsilon greedy algorithm. Put simply, the closer epsilon is to 0, the more control the neural networks have over the snake. If it is 0, the network will have full control. If it's 1, the snake's actions will be entirely random. We can view such random behavior by adjusting the epsilon value as follows. As we can see, now that epsilon is 1, as shown under the network, the rewards have dropped dramatically as the snake can no longer act in an opportune way. If you look to the left of the reward graph, you will see a graph displaying the average error per training cycle of the main network in the system. Currently, this error is consistently 0 since the system is in inference mode, as shown under the neural network. Should we put the network in training mode, we will see the training error showing again. You may notice that now, wait, hang on a second, it actually does work, wait. You may notice that now the state structure present within the input layer of the network does not necessarily correspond to what we see. It did a second ago, that wasn't meant to happen, that was a coincidence. But if we look at where the food is now, the food is to the right of the snake. However, if we look at the input layer of the network, we see the first 4 neurons show that the below and left neurons are lit up, implying that the food would be below and to the left of the snake. However, we know that this is not the case. This is because in training mode, the network is sampling from its experience replay memory buffer. So in this moment, the state that we are seeing at the beginning of the network is one of its previous memories which it is remembering in order to train and diversify and decorrelate its training data. The purpose of the experience replay is highlighted here. The primary aim of this research, however, is to explore if loading a new agent with a pre-generated experience replay could kickstart its performance upon deployment. To demo this, I will restart the program and make a new agent. For purposes of demonstration, I will leave the agent to act in the environment momentarily. We can see that the agent has no understanding of the game. It is consistently dying and does not know how to reach the food. We could leave it to train, which would ideally result in performance similar to that of the previous model. However, we will now load the replay. I will pause the system and go to File. If I wanted to see the previous model again, I could load it through the Load Model option. However, I will load an experience replay generated by another agent and fit it to the new agent through the Load Replay option. As we can see, there is no activity within the environment. However, the network is evidently learning. We will speed it up with the Rate option under Training and wait for it to finish. The amount of training loops to go is displayed below the network. I'm now going to slow down the training and give the network full control. As we can see, while being far from perfect, the network is performing much better than it was just now. Got stuck in a bit of a loop there. The agent is performing noticeably better within the environment than it was based only on its training with the loaded experience replay. I will now press File above the error chart in order to see how the training error has changed over time by exporting the graph. Here we can see its error data in graph form. In terms of implementation, all neural networks, the resultant Q networks, and the other components of the deep Q learning system were implemented manually in Java, including the multivariable calculus and linear algebra aspects of the program. The user interface was developed through JavaFX, and the graphs, which was just displayed a second ago, was implemented through Python. Thank you very much. I hope you enjoyed my presentation. Thank you.